In this video, we'll discuss how to make a turret with an offset aim joint. That is, the aim joint that is rotating, which is this little red joint here, is not aligned with the turret's barrel, but instead sits at an offset to the barrel. This is in response to a question created about aiming a turret with an offset aim joint in the UE4 forums. I found this question particularly interesting, and after exploring it a bit, I came up with a working solution. First thing I want to do is to show you the final result of this effort. Here we have a turret that can rotate to point at the target. So it's going to keep rotating towards the target no matter where the target is. So I can just go ahead and play with the target for a minute, and I can put it anywhere I want in the scene and it will move to rotate towards it. Furthermore, I can rotate the actor itself in some arbitrary rotation, and it will still be able to rotate towards the target. I can scale the actor too, and it will still maintain its rotation towards the target. Now, the project that I'm working with is something you can download for yourself. There should be a link in the description. It's on GitHub. You can use anything you find interesting in this project for your own purposes, and the project was built for UE4 4.17. Now that that's out of the way, I'd like to show you how the offset turret rotation is different from rotating a normal turret. So in this project we have a demo map, and when we open the demo map, the first thing that we're going to see is the final working version of the turret again. Moving to the next room, we see two different turrets, one without an offset and one with an offset. Now you can see that when we don't have an offset aim joint, I can go ahead and use the function find look at rotation. So just give me a second to open that up. So here in this function called rotate to face target actor, we are indeed using the function find look at rotation using the aim joint, which is this little red thing right here, and using the target actor, which is this pink ball here. So this works as expected for the turret without an offset aim joint, because this aim joint is aligned with the turret. So find look at rotation works just fine. But this other turret, let me open it up really quick. This other turret is also using find look at rotation. But since there is an offset, it's not going to work 100%. It's always going to be a little off. And if I go here, excuse me, just one second. If I go here and I increase the offset, you can see that it's way worse, and it's still not pointing towards the target. Moving on, let's look how to solve the pitch, or the angle in the ZX plane. This setup I'm currently looking at will only work as long as you don't move the Y coordinates of the target. So if I move X and Z like so, it will continue to work. But as soon as I move Y, it's not going to work. We'll fix that in a bit, but for right now I just want to focus on the pitch. So before diving into the code for this solution, I'd like to try to think about certain properties that the solution should have. First of all, we should be able to move the green box along this ray without changing the pitch. So give me one moment. And the barrel start here is the green cube. So we will move it along here, and as you can see, the system still maintains the appropriate rotation. The pitch that is required to rotate the turret doesn't change because we're still moving along this ray. Even if we move in some kind of negative displacement, it still handles that just fine. Furthermore, if we move the blue block along this ray, it'll still work. So it'll work with arbitrary lengths too. And give me a moment to disconnect the target actor from the turret. And let's put this turret in a strange orientation here. I'm going to move it up a little bit for the start, and I'm going to move the barrel end down a little bit. So now we have a really interesting orientation. And if I connect the turret back to the target again, it will still work. So those are all the features we're going to explore. But before going into the math or into the code for this solution, I'd like to just take a moment to further explain the problem visually. Okay, so now we're going to walk through how to calculate the pitch visually for this turret. Now, the larger problem is that we need to find the pitch for the target that could exist at any position within this white space. That problem may be a little too complicated to solve at once, so instead let's simplify the problem and just say that the target exists within this smaller circle for right now. So let's say the target is going to live here. Given that's the case, what we can do is we can draw a red line from the aim joint to the barrel end, and another red line from the aim joint to the target. Now, this will give us an angle, theta, between these two vectors. And this angle will represent the pitch for this case. After we find the pitch, we can draw a blue line from the aim joint to the barrel end, and we can now show that we can rotate the turret to meet the target, just like that. So what this means is that we can actually rotate the turret to meet any point along this circle, not just the target. So the target, its distance from the aim joint, defines the circle. And once we know that, we can just find the pitch for any point along this circle. Now that's all well and good for the simple case, where the target is somewhere along this smaller circle. But that doesn't solve the overall problem, which is this target could exist anywhere within this outer space. So for now, let's just say that the target exists at some point within this outer circle. Let's say the target exists here. Now what we can do is we can draw another red line from the aim joint to the target. But now we have a problem. We don't know where the other red line should go. But what we can do is we can find out. We can draw an orange line from the barrel start to the edge of the circle. And now we can go and draw a red line from the aim joint to where the orange line meets the edge of the circle. And once again, we can find that there's an angle between these two vectors. And this angle represents theta, or the pitch that we need to rotate the turret. And as a last step, let's just go ahead and draw a blue line from the aim joint to where the orange joint, or where the orange line meets the circle. And that is all the information we need to rotate the turret to meet any point along the outer circle. So the point is, if we know how far the target is from the aim joint, we can find a circle that has a radius that is the same as the distance from the aim joint to the target. Then we can find where our orange line meets the edge of the circle, and that will give us our second red line. And then we can find the blue line from the aim joint to where, again, the orange line meets the circle. Overall, if you have a hard geometric problem, it's good to, number one, try to solve a simpler version of that problem first, and number two, try to solve the problem visually before you get into the math. Now that we've had a chance to explain the problem visually, let's start introducing symbols and explain the problem mathematically. So I'm going to back out a little bit, and I'm going to explain what these symbols mean, and I'm going to explain what we're trying to find. So J is the aim joint, S is the start of the barrel, E is the end of the barrel, R is the barrel ray, E minus S. So it's a unit vector from S that extends towards E. Once we have the barrel ray, we don't really care about E anymore. The only purpose E has is to help us find the barrel ray. T is the target. Now you can see that there's this circle that encircles just the aim joint. This circle has a radius. The radius of this circle is equal to the magnitude of T minus J. Just keep that in mind. So all of these are bold, so they're vectors. And our scalars are not bolded. D is the barrel ray distance we are trying to find. So D is the distance from the start here to where we have this f of d point. So f of d is a function that gives us a point at distance d along the barrel ray. So we have s plus r times d. So this would be f of d over 2 because it's halfway between the start and the end. And this is just f of d. So we're trying to find here, we're looking for a scalar value d such that the magnitude of f of d minus j is equal to the magnitude of t minus j. That would mean that the distance from here to here would be equal to the radius of this circle. And once we have that, we can very easily find the pitch, which would be the angle between these two vectors. And again, the magnitude function is just v dot size because these are 2D vectors, which is just the square root of all the components squared and added together. So again, we are trying to find the distance d along the barrel ray here, r, that we need to travel until we find a point that is as far from the aim joint as the target. So we're trying to find f of d, specifically trying to find a d that'll give us f of d. So here we're just rewriting the equation. We're trying to find a value of d that solves this equation. F of d minus j equals t minus j, or the magnitudes of these are equal. So, as I mentioned before, the magnitude function here is just the square root of all of our components squared and added together. So we can expand these by, putting a radical here and squaring each of our components. And then we can very easily just square both sides just to get rid of the radical. Now, f of d is equal to s plus rd, so we can break up these into x and y components. Now f of dx squared gives us this squared, and if you recall from high school, a plus b squared equals a plus b times a plus b equals a squared plus 2ab plus b squared. So we have two components here. So this part squared and then 2 times a, and this would be b in this case, 2 times sx rx d plus r squared d squared. So we can use this to help us expand this. So we have f of dx minus jx squared here. And we can use this property of the binomial factoring to give us a squared minus 2ab plus b squared. And we can use this part right here to look at this and give us f of dx squared minus 2 of f of dx jx plus jx squared. And once we have that, we're looking at this f of dx squared that we just expanded up here. So we can take this part and substitute it right down here. Furthermore, f of dx is defined up here, so we can take this part and substitute it here. And these two lines are the same, except this just expands this out just a little bit. Here we're rearranging our components, so jx is just moving down here. This term is just moving a little bit. This term is moving. Plus, and then this term moves here. This term moves here. So we're just rearranging the equation. And the reason we're doing that is because we can simplify this term here, or this little expression, down to here. And the reason we can go from here to here is because we know that binomials can be factored in this way, and so we can just work backwards. So f of dx minus jx, which is just one part of this big equation, is this blue part here. And since x and y are pretty much the same thing, you just kind of switch your component. We can do the exact same thing with f of dy minus j squared. So these are the same, except you just switch the x's and the y's. Now, this is the same as this, except it's just colored a little bit differently. And then we can take these sections and substitute them by color. And the only reason I'm coloring them is it's kind of hard to read it without it being colored. And this and this are the same, it's just rearranged a little bit. So you can kind of follow where all the terms come from. R of x squared times d squared lives here, and then like r of y squared d squared lives here. 2sx rx moves down here, 2jx rx moves here, this moves here, this moves here, this moves over here, this moves over here. And the reason we're putting it into this form is because this is actually a quadratic. So ax squared plus bx plus c equals 0. So x in this case is d. So this whole mess right here is a. This whole mess right here is b. And this whole mess right here is c. And we've declared that accordingly down here. So now that we know it's a quadratic, we can solve it with the quadratic formula. And I'll show you how to do that in the code here in a minute. So now that we've had a chance to look at the problem visually and mathematically, I'd like to be able to jump into the code here and explain the implementation. But first I want to revisit this guy over here. And if we open him up, we can see that inside rotate to face target actor, he's using find look at rotation. But this guy over here, if we open him up, inside rotate to face target actor, he's using calculate turret pitch. So give me one moment. So this node graph gets executed every time I move the pink ball, and calculate turret pitch is executed. So inside calculate turret pitch, we're sending in the aim joint, the barrel start, the barrel end, and the target. So what I'd like to do is to now, give me one moment, jump into the C++ code for that function, which is right here. So here I have the mathematical explanation, and here I have the code. So you can see that this is a 2D problem. So the very first thing I do is I take these 3D vectors and I turn them into 2D vectors because I only care about the X and Z components. The next thing I do is I try to make sure I have a valid target location. I'm going to briefly skip over this, but keep it in the back of your mind. The next thing we do is we find the barrel ray distance. So here we're always looking for D, we're always looking for D. This will calculate D, the barrel ray distance, for you. Once we have that, we can easily find the scaled barrel end location. So f of D here is the same as the scaled barrel end location. And once we have that, we have the aim joint to scaled barreled end and aim joint to target. So f of D minus J is aim joint to scaled barrel end, and T minus J is aim joint to target. And once we have these two vectors here, these two vectors, we find the angle to rotate between them. And then that's our pitch. So let's jump into here where we find the value D. Calculate barrel ray distance. So this appears very similar to what we have over here. J is the aim joint, S is the barrel start, E is the barrel end, etc. We're trying to find D so that this equation holds. And then it says after a lot of algebra and after all that, we have A, B, and C. So we need to calculate these coefficients, and that's what this function does. And then the next thing we do is we need to calculate x1 and x2, also known as d1 and d2. Because it's a quadratic, we have two results, and since we need one distance, we select the best result out of those two. So if I open up calculate quadratic coefficients, it kind of maps to what this is doing right here. A has one term and another term. B has a blue part and then a green part. And C has four terms, 1, 2, 3, 4. 1, 2, 3, 3, 4. And so we just add all those up and we can calculate A, B, and C. After we do that, we can calculate the quadratic roots. So this is based on the quadratic formula. If you forgot what that was, it's here. It's x1 and x2 really is equal to this. And x1 uses plus and then x2 uses minus or whatever. So the denominator is 2a right here. So if that's nearly 0, then we're done. The radical input is b squared minus 4ac. It's right here. If that's less than 0, then it's invalid for the square root. So radical just takes the square root of the radical input. x1 says negative b minus the radical over the denominator, and then x2 is negative b plus the radical over the denominator. And then we have x1 and x2. After we found those, we just select the best one. So if we have a distance that is positive, that means it's out in front of this barrel ray. If it's negative, it means it's behind the barrel ray. So if we have two negative results, we just pick whichever one is closer to the barrel start. I don't know if that even happens, but hey, I got a code for the case, you know. Usually, I think this happens, is one of these comes in as negative and one of them comes in as positive, and if that's the case, you just return whichever one is larger. And then if one is barely greater than 0 and the other one is a nice big positive number, then you probably just want to select that one too. That will give us the distance from the quadratic. And then again, we calculate the scaled barrel end location, that's f of d. So f of d is s plus rd, and we have that right here. S is the barrel start, plus r times d, barrel raised r. And then we calculate the angle between these two vectors. So first thing we do is normalize the vectors. We calculate the angle between the vectors normalized. And then we say, should I turn clockwise or should I turn counterclockwise? And you want to turn whichever way is shorter, basically. So if I look here at calculate angle between normalized vectors, it references the geometric definition of the dot product. So here, Wikipedia, dot product, geometric definition. A dot B is the length of A times the length of B times the cosine of the angle between them. Since these are normalized, that turns out to be 1 times cosine. So when we get the dot product, by the way, in UE4, this is just shorthand for dot product. You just put that bar there. You can also do, once we have the dot product, we don't care about these because they're both 1. And then you just do a cosine of the dot product, and that'll give you the angle. And then should turn counterclockwise to meet. Says, okay, let me get this first vector here. Let me rotate it 90 degrees, so it's pointing somewhere out here. And, well, let me back up a second. For dot product, if it's positive, that means that the second vector is somewhere in front of the first vector. If it's 0, it means the second vector is directly perpendicular to the first. And if it's less than 0, then the second vector is somehow behind the first vector. So if we get the first vector and we rotate it 90 degrees, we're going to have a vector starting from here and pointing out here. And then, you know, if anything, well, actually, it would be like here. If anything, if there's a second vector that's anywhere inside this region, it'll be positive. And anywhere inside this region, it'll be negative. So positive means, hey, turn counterclockwise. And negative means, hey, just turn clockwise. So once we have that, we can find our pitch. So there's this part I went over and I briefly skipped called calculate nearest valid location 2D. So basically the target, if it's out here, if it's far enough away from the turret, we can make the turret point at the target. But if the target is too close to the turret, like if the target is around here, there's not a lot you can do about it. And we had to define some kind of behavior for that case. So we said, okay, if the target is like here, just extend it outwards. So it's somewhere in front of the closest joint. You can define your own behavior for this. This is what that kind of behavior looks like. So if I jump over here again to this turret, actually give me a second. Sorry about that. If you jump over here to this turret, I can go up here, and then when this ball gets too close to the aim joint, it's going to be invalid. So it just kind of behaves the best it can in that case. Is it right? Is it wrong? I don't know. It's undefined in my opinion. So that was everything about the pitch. And as you can tell, this video is kind of long. So I want to very briefly cover these other two cases. And if you really want a more detailed explanation, you can just look in the code because it's heavily commented. And I try to put very readable variable names in there. So it should... You should be able to just read this and learn from it. So for calculating the pitch and the yaw, basically this is a 2D problem and this is something in 3D space. So what we do is we rotate the turret yaw first, and then once we rotate the turret yaw first, we have it lined up so that it exists on a 2D plane. And then once it exists on the 2D plane, we can just call the function we had before, and it'll just work. Now the problem with this implementation is that if you rotate the turret, it won't point at the target anymore. But that's okay, because this one will fix it. So if I rotate this, it takes in the actor transform. So you can go ahead and do whatever you want with this guy, and it'll handle it. Again, I'm not really going to cover it because this video is just too long anyway. But it is covered if you want to look in the code. And this is just a little demo to show you. You can kind of just transform your turrets any way you want, and it'll just work. So you can go ahead and kind of test it out and play with it if you want. If you have any questions, leave them in the comment of this video, or leave them in the comment section of this video. I hope you learned something, and hope you have a great day.